Okay, so good morning, good afternoon, everyone. So I'm glad to introduce my student here in Campinas, joint with Christian Martinez, Daniel Bernal, currently at the University of Edinburgh. So Daniel, please go ahead.
Thank you very much, Professor, and thank you for the invitation and for letting me do this smooth presentation. I want to talk a little bit about some Bridgeland wall crossings for some moduli spaces of objects on the derived category of P3. And yeah, so I work with some Bridgeland stability. That's the main work in my thesis. And Bridgeland stability comes as a generalization of the usual mu stability for sheaves. But here we have like a counterpart. We have to work with some complexes instead of complexes of sheaves instead of just sheaves, right? But everything that comes relatively naturally, and the definitions are relatively the same. So let me start by fixing some notation. So here X will be the node P3 over a algebraically closed field C, or a smooth projective fan of threefold which has Picard rank 1, and his sample generator is going to be H. I will call dBx as the derived category of coherent sheaves on X. And I also will call by CHA, I will denote the Chern character of the object A. That is going to be the serious Chern character with the intersection of the generator in the corresponding degree. For every complex, every A in the derived category. So it's a complex of sheaves, and then we can define the Chern character of the complex as the alternating sum of the Chern character of each one of the elements of the complex. And if I have beta a real number, then I can twist that Chern character by adding like a factor that's going to be the exponential of minus beta times the generator H times the Chern character of A. And with this twisted Chern character, we can define a twisted Mumford slope, right? So our Mumford slope is going to be the first Chern character twisted over the zeroth Chern character twisted if the zeroth Chern character is non-zero, and it's going to be plus infinity if if the zeroth character Chern character twisted is going to be 0. Okay. In this case, the zeroth Chern character and the zeroth Chern character twisted are going to be the same. Okay, so we just change a little bit linearly the first Chern character. Okay, so start with some preliminaries. In general, to obtain Bridgeland stability conditions is a hard task, and there have been obtained for curves. And in the case of curves, there is known that the Bridgeland moduli space coincides with the usual mu moduli space, or Giesecke moduli space. For surfaces, we have to do a first process that is called a tilting. And when we want to work on threefolds, we have to do what's called the Bayer-Makritoda double tilt construction. So we do the same tilt twice. So in the first tilt, what do? We start in the category, in the valence category of coherent shifts, and we have a slope that we call mu beta. That's the one that we just defined. And then we can split the category of coherent shifts into a torsion pair. Torsion pair tau beta and f beta, where tau beta are going to be all the coherent shifts such that their twisted Mumford slope is greater than 0 for every quotient. And f of beta is going to be all the coherent shifts, which mu beta of f is going to be less or equal than 0 for all sub-shifts f. right? Okay, and if we do the extension generated category by elements in f beta shifted by 1 and tau beta, we obtain a new heart of a T structure. And we call this new heart as co-beta of X, right? And in that co-beta, we can define a new slope that we call mu beta alpha. That depends now in two parameters. The parameter beta, that's going to be a real number, and alpha, that's going to be a positive real number. And it's essentially this formula here. It's like the second shared character minus alpha squared over 2, the zero shared character, over alpha, the first shared character of the object, whenever the first shared character is non-zero, and plus infinity when it's 0. Okay, so we obtained a new heart, and we ask ourselves, maybe this is a Bridgeland stability condition. It is not. So we have to do this again. And once we do exactly the same, we start with co-beta X. We have that slope, mu beta alpha, and then we once again split co-beta into a torsion pair, tau beta alpha and f beta alpha. That's essentially the same definition as before, but here we just use the slope that we have for exactly the same for quotients of E. That's right now is going to be a complex, or F that's going to be a subcomplex or original complex E. And with that torsion pair, then we make the extension generated category, and we obtain a new heart of a T structure. And in that heart, we obtain a new slope, lambda beta alpha s, that is going to have this expression. And that it seems like very abstract and very arbitrary, maybe. It comes from a very well-defined equation in terms of the Chern characters and exponential. Okay, so we have a notion of a slope in a category that's a heart of dBx, and then we can consider stability with that slope. We can consider which objects are lambda stable or are not lambda stable. And when in surfaces that constructed some stability conditions, they obtain that when you make one of the parameters very large, then you obtain that the Bridgeland moduli space coincides with the Gieseker moduli space as well, right? We have something a bit weaker than in curves, because in curves everything is just essentially the same as the Gieseker moduli space, but here in surfaces you obtain, like when you go to the infinity in a way, you obtain that is the Gieseker moduli space. And in the paper made by Professor Anthony, Professor Marcos, and Martinez in 2023, they defined what's going to be an asymptotic stability, a notion of stability in a slice of the set of stability conditions in terms of curves. So essentially, if you take a curve in that slice, you say that something is asymptotically stable along that curve if after a point, all the elements belong in the category, and after a point that's going after that initial point, every sub-object has to have lambda less or equal than the original one. So essentially says that at a certain point, nothing can destabilize. And that's what they defined in that paper. And moreover, they also described where were going to be all the lambda semi-stable objects along vertical curves. Beta equal a beta line. They were characterized. They gave some criteria for when those objects are lambda semi-stable, and when they are lambda semi-stable, what type of information can we obtain? Even more, they also described all such objects, all asymptotically lambda semi-stable objects, along beta equals 0, so vertically in that line, for two Chern characters, the Chern characters minus 2010 and minus 2020, that are going to be essentially shifts of instanton shifts, duals of those instanton shifts as well. Even more, they also describe all walls for the churn character, the shifted churn, the twisted churn character minus R0, D0 in the alpha S slice. They describe all walls. And they gave this equation. All walls have this equation. S plus 1/6 over alpha squared is going to be the third churn character over the first churn character. Great. And even more, they obtain that they are disjoint. They are disjoint. So this is kind of strong. This is kind of strong. Okay, just by a note aside, what do I mean by a wall? Well, if I have an object E, we can have two types of walls for E. The first one is a numerical wall. And a numerical wall is just going to be the set of solutions of lambda F equals to lambda E. So we know that in a certain set of stability conditions, lambda E, if E is stable, then lambda of F has to be less or equal to lambda of E if F is a sub-object, of course. And if it's going to stop being semi-stable somewhere, then they have to be equal. So our first potential candidates are going to be these numerical conditions. And the second one is to give formally the existence of a short exact sequence in the category that show you that, well, there is an object that in fact stabilizes in that category. But walls can be very strange. So what they obtain to be disjoint is really good. Well, they can exhibit a lot of phenomena. They can intersect each other, like this case. The red one, the black ones are two different walls, and they intersect. In, for example, this is the beta alpha slice, and S is 1/3. They can also accumulate towards a point. So we don't know which ones are actual and which ones are numerical. In this case, they know, but in general, it's a bit hard. And we can play with the type of slope we work. So we can have lambda walls, or we can have new walls, or we can have new walls, right? And they behave, the moduli spaces, they parameterize in a sense, they vary as well. So to obtain that they are disjoint, it's very good. And in this case, well, I'm going to call chamber a subset of a slice where the moduli spaces do not change. They are isomorphic. Okay. With this in mind, they also proved a Bertrand's type lemma that essentially says that if I have that the churn character of E is going to be minus R0 D0, then to destabilize at one point is exactly the same as to destabilize at all wall. So there is a point where an object A destabilizes the object E, then that object A has to destabilize at all points of the wall, of the numerical wall. And using this, and using the support property of the Bridgeland stability conditions, and taking some limits, then we obtain that if the churn character of the destabilizing object is R, C, D, and E, then we obtain three numerical conditions for that restrict which are the possible churn characters of that destabilizing objects. That's what they obtained, right? Even more, when beta equals 0, they also found a quiver region. A quiver region that's going to be this region. And in this case, the moduli spaces are going to be projected. I'm going to talk a little bit more about quiver regions in the following. And they also gave some integral conditions for the churn characters that are going to destabilize. So we can, in a way, describe numerically what are going to be the churn characters of the destabilizing objects. And there are these three conditions that come essentially from the relations of the churn character and the churn classes. And the Euler characteristic. They also gave a Killing wall, alpha 0 equals 1, where below that wall there is nothing stable, and I'm going to talk about it just a little bit more as well. And they also gave the existence of an instant wall, so where everything that crosses, everything that survives after crossing that wall is going to be instanton. And well, what I just mentioned, there is also a Gieseker chamber in this case. When R is 0 and alpha is very big, then the last chamber is going to be the Gieseker chamber. That's where the Bridgeland moduli space coincides exactly with the Gieseker moduli space for Sheaves. Okay. They also, when beta was 0 and the Chern character is 0030, they described all the actual and numerical walls. So these two are going to be the numerical and actual walls in this case. The ones that shaded is going to be a chamber. And the ones that shaded in this part is going to be the quiver region in this case. Even more, they also gave all possible destabilizing sequences for those two walls. So they gave you by hand, and that's how you show that a wall is actual in this case. So one was destabilized by the structural shift of planar curve, cubic planar curve, and the other one has a lot of possible destabilizing objects. Okay. They also studied the cases of -2010 and -2020. That are the cases of instantons of rank 2, if I'm not mistaken. And they gave all the wall and chamber decomposition in the alpha S slice. Okay, let's talk a little bit about instantons. So if I have X Fano threefold of Picard rank 1, as the Picard is generated by H of X, then we know that K of X is minus IX by minus an integer times the generator, and we call IX the index, and if we divide it by 2, we obtain two other numbers that we call QX and EX, and we call IX the index. In a paper by Comas and Jardin, they defined though it's going to be an instanton shift on X. And we say that a mu semi-stable shift E on X is instanton. First, if the Chern character is going to be minus EX times the half of the rank. And second one, that if the first cohomology and the second cohomology of E twisted by minus QX is going to be 0. So this generalizes other definitions of instanton bundles that were given by Daniel Faenzi and Kuznetsov as well. Yeah. So if we want to do something similar with Bridgeland stability, we can obtain a small generalization of what instanton is. So if I fix beta 0 equals minus EX over 2, and then I consider an object E that when I twist the Chern character of the minus R0 T0, and I obtain the following region, there's going to be the region where of all alpha S, such that alpha and S is going to be greater than 0, and that those points that belong to that condition. Then whenever I take a chamber that intersects the region, I'm going to call an object C instanton if he's going to be Bridgeland semi-stable with respect to a stability condition in that chamber. So essentially is that. So you can take any chamber that intersects that region, and if it's going to be semi-stable with respect a condition in that chamber, well, that's as an instanton, right? Okay. they also prove some properties. If we acceded on the alpha S slice, then first we have that E is Bridgeland stable. If E is also Bridgeland stable in the outermost chamber, then it has to be stable in all intermediary chambers. So if it's as an instanton, which is also Bridgeland stable in the infinity in some sense, then it's going to be Bridgeland stable in all intermediary chambers. E is going to be as an instanton if and only if it's dual, it's going to be as an instanton. And by its dual, I'm calling the functor, the right derived functor of E minus EX twisted by 2. So it's like a slightly different version of duality. Also, he has to be he has to belong to the orthogonal category of OQX. And there's in fact a generalization, so to the definition that they gave, right? So if we have the first cohomology or the second cohomology of I minus QX, well, this is just the xi of OE minus QX. And well, you pass the QX to the other side, and that's essentially the definition to belong to the orthogonal category, right? Generated by OQX. And even more, well, we know that in P3, and if we take the Chern character 0030, we just have two walls, right? So exactly. So when we cross the first wall, everything that stays there is going to be as an instanton, because that's a chamber that intersects the region U in our case. Maybe I forgot to tell it, but when we are in P3, our index is 2. So if our index is 4, I'm sorry, our index is 4. And if our index is 4, well, this is going to be 1/6 over 2 over 2, well, over 4. And it's going to be way in front that the region that I shaded just a few slides ago. Okay. Great. So every object that crosses that wall is going to be as an instanton. So I just take they just took one of such objects that's going to be defined by an extension of H21 OH minus 1 shifted by 1. And they constructed the first sequence 301 to K to OH minus 1. And with that one, and making some small tricks, you obtain another sequence that goes from K to 60 to G. And with that one, you can construct the other sequence G to 301 to OH2. And just composing in the diagonal, you obtain a monadic representation of a same instanton, of that same instanton A. Similarly, we would like to know how much of this can be done for other Ds. So for doing that, we also computed all the numerical walls when beta equals 0. So we made a small program in Sage that allows us to compute all with the numerical conditions we just gave. The numerical conditions gave all the possible Chern characters and the corresponding walls. Okay. And with that, we can do exactly the same for the Chern character 0040. And that's what we did. And we obtained that there are 3 walls. Alpha 0 equals 2. Alpha 0 equals square root of 7. And alpha 0 equals 1. That has a lot of multiplicities, right? And they are destabilized respectively by O2, by OH2 of a planar curve of degree 4, and 1. The other one's highly destabilized. Everything is destabilized in that wall. Right? So these are the 3 lines, the 3 walls, but we also show that they are actual as well. So they are numerical and they are actual as well. And the blue region is going to be the quiver region. And if we consider an object that crosses the first wall, it is not still as an instanton. But if we cross the second wall, then it's going to be as an instanton, right? So the object that destabilizes in the alpha 0 equals 2 is going to be an extension, the one is in the first line, right? It's going to be an extension of the ideal by the O2, right? So that's going to be as an instanton object. And we did some kind of similar process to that one. And we construct a very specific alpha that allows us to have the cokernel, the ideal of the elliptic curve of degree 4. And with the second Euler sequence, we obtain this vertical short exact sequence. And we can also obtain the horizontal one that goes from the omega-1 to 401 to O2. And once again, if we just compose in the diagonal and we make the necessary computations, verify, you know, that this is going to be, in fact, monadic type representation of E. So the instantons, they are known to be well-known cohomology of monads. But in this case, they are complexes. So these instantons are a bit weaker, right? So they're just quasi-isomorphic to almost a monad. And we expect that most of the instanton objects, if not all, are also represented in something like this. Well, now let me talk a little bit about some quiver regions. So essentially, what's a quiver region? So if I have E1 until Tn, En, a full X exceptional collection, yeah. Then we have two definitions. The first one is, we say that E satisfies the upper half plane condition if there is a real number phi, such that the extension generated category by E is going to be the slice, is going to be exactly the same as the slice of the stability condition, of a stability condition, going from phi to phi plus 1. This essentially says to us that if we have exceptional collection and we can find a hyperplane that contains the slopes of all of them, then that exceptional collection, in a way, that exceptional collection satisfies the upper half plane condition. And I'm going to take a subset of the set of all Bridgeland stability conditions, and that subset is going to be a quiver region of that exceptional collection if every stability condition in the region satisfies the upper half plane condition. So what really means to satisfy the upper half plane condition? It means that, in a way, every object can be written as an extension of those objects. And when we represent the extension of those objects in a diagram, we obtain a quiver representation. So in a sense, every object has a quiver representation associated to it. And to study, in a sense, lambda stability with respect to the Bridgeland stability condition becomes essentially the same to studying the stability for quivers representation, that we know that those spaces are projective and such. Perfect. Well, Preti, he also gave a criterion for describing quiver agents in a very general setting. So I'm going to mention it here. So we have E, full X exceptional collection in the derived category, such that the elements belong into maybe not all the upper half plane, but maybe the upper and the lower half plane, that all of them are in that place. Then E is going to satisfy the upper half plane condition with respect to one stability condition if I can find an index such that that stability condition is inside all the lambda walls, EI shifted -1, EJ shifted -1, by all elements that are in the lower half plane. And if phi is going to be outside the walls, lambda ei minus 1, ek, for all ek that belong in the upper half plane. Okay. And even more, this is an example that he did. This is some application of that proposition and how to find in some quiver region. So the orange walls are for a specific case, and the green walls are for a specific case. So you take what things are inside the walls and what things are outside the walls of the exceptional collection. When you just take the usual exceptional collection for DVP3, that's going to be O minus 2, O minus 1, O, and O1, and any shifts of that one. Yeah, so those are the lambda walls for that exceptional collection, and using that proposition. Right. However, we proved a bit of a weaker version of that proposition by Preti with some past technique that has been used. Essentially, is the following: if we have E, there's going to be E1 to EK, full strong exceptional collection for the derived category, such that all EI are going to be lambda stable objects, and the EI can belong once again to the category shifted by -1 or to the category. And if the maximum of the elements that belong to the lower part, in a sense, of the plane in the lambdas is less or equal than the minimum of the ones that are on the upper side, then lambda stability of E is equivalent to king theta stability for that quiver. But E here, maybe I forgot to write, I'm sorry, that E here has to have the Chern character minus R0 D0. Okay, yeah. Perfect. And there have been two uses of that kind of proposition. The first one is the one that I mentioned before. When beta equals 0, x is P3, then there are no walls in that region. And when I consider it as a subset of the alpha S slice. So yeah, everything dies after that last wall. And that's what we call a killing wall. Because there are no walls, and the moduli space after that is empty. So there is nothing. And also in a paper by Comachi, Jardín, Martinez, and Mood in 2023, when they took beta equals -1/2, and they took x to be a quartic inside P4, then there is a quiver region. They obtain a quiver region using that one. And everything instanton also writes itself as the cohomology of that monad, the type monad, right? Okay, right, yeah, of course. Using the first one, no, not that one. No. So using some similar techniques with what they used, we obtain some killing region for beta different than 0. So we are not specifically treating with same instantons here, right? But even though we can also get some type of quiver region. So here I'm going to ask beta between -1/2 and 0, and I'm going to ask x to be P3. So our first proposition is that there are no walls for the Chern character -R0 D0 in the region Q given by 3 beta squared less than 6s plus 1 alpha squared 6 less than 1, considered as a subset of the alpha S slice. And the second one is the following one is a quiver region. So all the alpha S such that there are between 1 and 3 times the minimum of alpha I squared, where alpha I are going to be the positive roots of a very strange polynomial. So that polynomial is going to be the solution of a numerical wall, So essentially, that's going to be a quiver region. And if we apply this to our case, well, we obtain the following. We obtain when beta is minus 1/3. Well, the blue one is going to be a killing wall in a sense, right? We don't know what happens in the white part, but in the red part, we know that the moduli space is empty. And in the green part, we know that everything has a quiver representation. So the moduli spaces here are very, very nice. And when beta is minus 1/10, well, our killing wall increases as expected, because when beta is 0, we know that everything that is going to die in that region, and our quiver region also decreases a little bit, right? But that proposition that we just had, this one, essentially says us that all beta alpha s that hold that condition, then we have that quiver region, right? As long as the objects stay in the category. So we can, we have essentially like a surface in the beta alpha s slice where every point that corresponds that's inside that quiver region coincides with the Bridgeland stability moduli space coincides with the quiver. Right? And if we try to do that, this is an example in the beta alpha s slice that shows one inequality. You just have to make the union of this region with the union of another region, and we obtain the total quiver region or quiver surface for P3 and minus beta between 1, -1/2, and 0. Well, I'm so sorry I ended very fast, but this is what I wanted to tell you. Thank you very much. Professor, you are silenced.
Yeah. Thank you, Daniel. It's no problem because now we have time for discussion.
Okay.
So maybe I start. What is this last picture that you shown again? I'm not sure I got it. What?
This one, yeah?
Yeah.
Yeah. So this is essentially the condition that this one. That the maximum of the EI of the alpha beta alpha is less or equal than this region, right? You just have to intersect that region with the region where the objects belong to the category, right? And then you obtain a quiver region for that one.
Okay, so that is the quiver region in 3-dimension alpha, beta, and S.
Exactly, in beta, alpha, and S. Exactly.
Okay.
In fact, we have to be a bit more deep, right? We have to do all the possibilities for the objects that belong in that category and all the corresponding possible inequalities that appear, and we joined that those 4 or 3 possibilities that appear. But this is one example of that application. Like this is one of those inequalities that appear.
Okay.
Exactly. But essentially, that's how you construct it. And you are going to obtain in all the beta alpha S slice, you're going to obtain a region where a surface, in a sense, where every point that belongs to that has a quiver representation.
Okay. So maybe one comment before I open for questions. If you go back to that graph that you have various walls, I think it was the 0040 case. Yeah, it was best. Yeah, this one. Yeah. So one thing that Daniel mentioned, forgot to mention, is that in the outermost chamber, right, beyond this largest wall that crosses the horizontal axis at 2.5, right? So in this outermost chamber, the Bridgeland moduli space coincides with the Gieseker moduli space, right? For one-dimensional sheaves with that Chern character. So essentially, one-dimensional sheaves for which the Hilbert polynomial is something like 4 times t plus 2, right? So this is the moduli space, and then the walls, they destabilize some of these sheaves until what remains in the blue region that Daniel is pointing now are just the instanton sheaves, the zero-dimensional, sorry, the so-called rank 0 instantons. But then the moduli space has more stuff, not just the rank 0 instantons, but also those complexes that Daniel mentioned a few slides afterwards, right? Are there any questions or more comments?
Yeah.
Yes,
I would like
Charles,
to make,
go ahead.
yeah, the definition that you have for a C instanton.
Yeah.
Yeah, is it made to so the object is the cohomology of a monad, or you have a
You don't know. You just have this definition. They have to be Bridgeland stable with respect to a condition. But there are some cases when you know that they are saying instanton. They have a monad representation. For example, we know that in P3, this last thing says us that essentially everything that is here in b equals 0, maybe. Yeah, maybe. This first result, it tells you that every instanton in fact has a monadic representation, and when you have that x is a quartic, well, every instanton also has a monadic representation, a monadic type representation, because this is not a monad, this is almost a monad. And we expect that if you take all Fano of Picard rank 1, this also holds. That's the hypothesis, right? But in general, you do not know that. You just know that the definition is that one, that it's Bridgeland stable with respect to a chamber that intersects that region U.
and more on that, there is a reason, a particular reason to call that instanton. Do you know it, or?
It's a because that other wall, if I'm not mistaken, Professor Marcos and Christian maybe correct me if I'm wrong, because that region U is going to be the instanton wall. So everything that crosses the wall and is not instanton dies. So the only things that remain in that chamber are going to be instantons that have not been destabilized. But there also appear some other things, some very strange things. You don't know what they are. We expect them to be deformations of instantons, but they also are Bridgeland stable, right? So that's why they're called C instantons, instantons in that chamber. That's how I think about them, at least.
Daniel, if you go to the next slide. Yeah. So so is there the slide where you put the definition of the instanton is the previous one?
That one.
Yeah. Okay, so the idea of the definition of instanton, Charles, is that usually instantons has 3 parts, right? So it's you fix some Chern character. So in our case, we fix this Chern character there, that CH0 of beta is of that form minus, so this is fixing the Chern character. Then there is some cohomological condition, which is in the next slide as the perpendicular for OQX, right? So this is the cohomological vanishing condition. And then there is a stability condition, which in our case, we adopt Bridgeland stability. Right? So in this sense that it imitates the definition of instanton adapted for this context of Bridgeland stability.
Okay.
And,
yeah, I was thinking, how can you produce that old definition from that neat other one from same stable? Thank you.
And it turns out
perhaps I should add a comment.
Sure. Yes. Go ahead.
Oh, it's okay. It's okay. No, go ahead, Marcus.
No. Go ahead, Christian. I'm speaking too much.
Oh yeah, I was saying that part of the idea why this Chern character, right, and why this twist, where it comes from the idea that if you take the right dual of an instanton, then you would like that to be an instanton. then we're just looking for this slice of stability conditions that somehow, when we do the right dual, right, then the chain character was at the same time, and that's how we get this condition on the chain character, and the right twist to take, which is beta 0, that Daniel will mention. So it's like looking at these ideas, right? That what happens if I do, like when I take the dual of an instanton, I would like that to be an instanton, and we were just looking for that region when that happens. And then we end up proving what Daniel was saying, right? If you have a sheaf, right? In this case, a sheaf of a sheaf that never got destabilized and stays stable in that chamber, then that sheaf has to be an instanton sheaf. So somehow, maybe it doesn't have all instantons, but it has a big part, at least the instantons that never got destabilized and are stable there, those sheaves has to be instanton sheaves. So it's like this.
Okay, nice. Thank you. And if I may, less fast question on the like almost monadic description that you have on the quadric like in the almost the last slide, yeah. There is an S. No, one more, I guess. No, some more, I guess. No more. The on the quadric. More.
On the quadric.
Yes.
Yeah.
Yes, that
one.
This is the spinner bundle.
Yes.
This is the spinner bundle.
The spinner bundle.
Exactly, that's the spinner bundle that appears in the exceptional collection of the derived category of the Q3. We know that it has OX, OX minus 1, OX1, and the spinner bundle minus 1. I think that's the exceptional collection in that case.
Okay.
So this
no good. So yeah,
in Daniele's paper about instantons on funnels, so he gives this as a monadic description for the instantons on the three-dimensional quadrics, right? So the if this complex only has cohomology in the middle, that is an instanton bundle in the sense of Daniele. And but in this context, this thing may not be a monad. It may pick up some cohomology in the OX position as well, right? So it may have a cohomology in the middle, but also a cohomology on the right, right?
Also, I should say that in the case of the quadric, there might be several notions of say instantons, because the notion of say instanton is that there is a chamber where the objects are stable, right? That are in that region that Daniel mentioned. Then for this monadic type description, right, that will give you a smaller region. Then you will need a chamber that intersects that region for you to get the monadic. But let's say that in the definition that we propose, there may be other notions of say instances that don't intersect this quiver region. So.
Yeah, the point is that we don't know whether there is some other wall that cuts the quiver region into 2 bits, right? Or if the quiver region is contained in a single chamber. So that's what we don't know, right?
But from the exceptional collection that you have, you could have another like monadic description with just the OX appear in the middle, right? I don't know if in that region, but in some, I don't know.
Yes, but that with the OX in the middle and OX1 on the right, right? So some kind of linear monad. That's not what Daniele calls an instanton on the quadric. Right? So those things with the linear monad, they are not instantons in Daniele's sense.
Okay, but could be in yours.
It could, well, yeah, I guess.
Yeah.
Yeah. It could be also, right? Have both being represented in both monads, right?
Yeah. Okay. Thank you. Thank you very much.
Questions or comments, anyone? Good. So I guess that's all we have for today. Thank you very much, Daniel, for your presentation. The next seminar will then be on October 8th, also a Tuesday, same time at 12 noon here in Campinas, and then 6 p.m. in Moscow,
Yes.
10 a.m. in Bogota, right? So October 8th. And the speaker will be Daniel, right? Alexander Daniel.
Yes, yes, right.
Yes. Yeah. So the next speaker will be Daniel Vasiliev, which is Alexander's student there in Moscow. Okay. So I'll send announcements and updates closer to the date. But let me stop recording.
Also, please send a link to records.